The time has come for us to shift our emphasis away from spanning trees and towards pathfinding algorithms. Today we're going to begin our foray into pathfinding algorithms by looking at Dijkstra's algorithm, a single source shortest path algorithm. You're watching another episode of Graph Theory. Hello and welcome back to Graph Theory. Today we're going to be looking at Dijkstra's algorithm, written in 1956 by Dijkstra. As mentioned, this is a single source shortest path algorithm, and basically the idea of this is that we start from a source node and we're trying to find the paths to all the other nodes in a graph. When this algorithm completes, what we'll end up with is we will know the distance from the source to any node in the graph, as well as a path to get there. Both these distances and these paths are of course minimized. So yeah, what we get at the end of the day is actually a tree, namely a shortest paths tree. So yeah, in fact there is not much more to say. Let us jump into tracing this algorithm. Alright, so let us take a look at the pseudocode for Dijkstra's algorithm. Now, for the first time ever in this series, we actually have code that is too long to fit on screen. So what we're going to do is first we're going to take a look at the code that, is involved with just preparing all the data structures. And well, it's convenient for us to look at things this way because all this preparation stuff just happens once. Once it's all done, we don't have to look at it again. So yeah, let's take this from the top. Let's try to get everything prepared before we jump into the actual trace. So for this algorithm, we need three data structures. First and foremost, a list of vertices, as well as two arrays to maintain information about the vertices, namely distances, which is a measure of the cumulative age weight from the source vertex to that particular destination vertex, as well as the parents, which will tell you which vertex leads up to this particular vertex. Don't worry if it's not clear now, it'll get clearer as we trace along. For all these three data structures, we first initialize all the distances to infinity and set all the parents to null. At the same time, we also add all the vertices to the vertex list. Then we set the distance to the starting node as 0. This of course makes sense because, well, if you start at A and you want to go to A, then you incur 0 distance. So yeah, here's how we're going to visualize all the different data structures. Basically, similarly to what we've seen before, we will not explicitly show the parent array. I'll indicate it in the form of arrows. The distances are shown in these boxes here. And as you can see, we are all ready for the first iteration. Our source node is going to be A, which is why we've set its weight to 0. Everything else is infinity. So then we can move on to the more important part, which is the actual algorithm. Essentially, what we're going to try and do per iteration of Dijkstra's algorithm is we're going to first find which vertex has the minimum distance as noted in this little box. We're going to look at its neighbors and basically propagate its distance out to its neighbors. Let's see how this works. So in our first iteration here, of course the smallest is A because its value is 0 in comparison to everything else that is infinity. We look at its neighbors, namely B and C. For this first iteration, it's very simple because the distance from A to B is simply the edge weight between A and B. So we're not going to actually trace the important part of the algorithm here. All I need you to understand at this point is the fact that, well, the distance from A to B is 5. The distance from A to C is 3. And these two numbers come directly from the edge weights. We show the parent relation by drawing a blue arrow. And the direction of the arrow simply says that A is the parent of B. So we are ready to move on to the next iteration. We want to find the vertex that is still in the vertex list with the minimum weight. So yeah, the next element we look at is C. So once again, we look at its neighbors, but we do not process the neighbor A because, well, the neighbor A is no longer in the vertex list. So notice what is happening here. Basically, the distance from A to F would be 3 plus 5. Of course, we don't go all the way back and trace it. We simply take the distance that has been accumulated at C and basically push that out. So yeah, as you can see, the distance at F is simply the distance at C plus the edge weight required to get from C to F, and therefore the distance at F is 8. This computation of course happens at this line. So yeah, we've basically taken the distance at C and pushed it out to E and F. We can now move on to the next iteration. We pick the smallest ones again, which is why we pick D. Now, something very interesting happens in this iteration. The neighbors we have to consider are D and E. But notice that when this part of the code actually runs, only D is updated. E is not. Let's try to understand why. If we were to go from A to B and to E, basically the total distance we've incurred is 5 plus 8. That means that to get to E, we have to go through a total of 13. This is actually not optimal because we've already found a path that is ACE that gives us a total weight of 12. That is why we actually do not choose this path. We do not set B as the parent of E. The part of the code that makes this decision is this conditional right here. We first compute the new distance, that is 5 plus 8, and then we check to see if this new distance is less than the distance that we have already computed. In this case, it is not. That is why we do not update the distance and we do not change the parent. C will remain the parent of E because that gives us a shorter path. So yeah, that is basically the decision making that goes into Dijkstra's algorithm. Let us now continue the trace. We of course pick F because F has the smallest distance so far. Once again, F pushes out and yeah, H is updated in a very normal way, but notice what has happened to E here. The distance at F is 8, therefore going from F to E makes the distance 10. This is actually better than the original path, which was 12. That is why we have actually removed this H. The best parent for E is now F, which is why we have reassigned it. The shortest path is now ACFE instead of ACE, because the HCE is very heavy. So yeah, we've basically exhausted the several different things that this algorithm can do. We can now pick up a little bit of speed and finish off the trace of this algorithm. Next, of course, we pick E. E will push out to its unvisited neighbors, in this case not going to D because that would make it 14. And of course, it also reaches out to G and H. Next, we go to D. D tries to push out, but you realize that nothing has happened because, well, none of these connections would be optimal. We move on to G. G can reach out to I, updating its weight to 19. Then we look at H. H doesn't update anything, and then we finally look at I. And that concludes the trace of Dijkstra's algorithm. You can sort of see the thought process here. In fact, we're going to go back very quickly and just redo the entire algorithm from the top down very quickly. Notice what is happening. All we are doing is we're starting from a particular point, we're grabbing the best weight and propagating it down. And as we are doing this, we may knock out certain edges that are not as good. What we end up with is what we call single source shortest paths. That is, from our source A, well, we can find the shortest path to every single node in this graph. If you pick any vertex at all, I can tell you what is the best way to get there and what is the distance you would incur to get there, and I can tell you that it is minimized. So yeah, that concludes our trace for Dijkstra's algorithm. Now, the more eagle-eyed among you will probably notice that what we have is actually a tree. In fact, what we have is a spanning tree. But remember that when we generate this tree, we are doing it from the point of view of a pathfinding algorithm, which is why the tree we get is not a minimum spanning tree. In this case, it's very easy to prove this because I could always throw out this edge in favor of this edge, and the sum of the edge weights has actually decreased. If we kept this connection here between B and D, the total edge weight sums up to 36. Making this replacement here gets it down to 31. Now, I haven't checked for sure to see if this is a real minimum spanning tree, but you get the idea. We have just proven that, well, the original tree we've gotten is not a minimum spanning tree. So yeah, that was the trace of Dijkstra's algorithm. And while this algorithm is great and all, there is actually one glaring issue with it, and that is the fact that you in fact cannot use it with a graph that has edges with negative edge weights. If you do that, you may end up with an incorrect result. This doesn't happen every time, but in general, Dijkstra's algorithm is not designed to handle negative edge weights. Let's see this in action and we'll understand why that is so. At first glance, it might be kinda counterintuitive. Why is it that a negative edge could create some problems? Well, let's trace it and see. Once again, we're gonna start from A and we're gonna, just visit every node on a graph. So as per normal, A propagates the weight down to B and C. Then our next node is B. Once again, we propagate its weight down to D. D is the next minimum one, which is why we check it. It doesn't lead to anywhere else, so we don't do anything else. And we move straight on to C. Now, C gives us this edge, which we realize is actually smaller. So, we update B. So we say that visiting node B by taking a detour to C is actually cheaper than going directly from A to B. And that's it. The algorithm terminates without updating the distance to D. Since we know that the distance to B is 1, then the distance to D should be 1 plus 2 equals to 3. But that does not happen. Notice that because the algorithm does not update any further linked nodes, what you end up with is a wrong distance at the end. So this is a very simple example to show you that, in Dijkstra's algorithm, if you have a negative edge, you run the risk of getting wrong results. To show you why this will never happen if you have a non-negative edge, let's jump to an earlier part in the trace. Let's say now we are nearly at the end of the algorithm, but we are looking at node C, and we want to check it against this edge. Its weight is now x, and let us say x is non-negative. If x is non-negative, then we'll know for sure that this distance can never be less than this distance. Because 9 plus x, whatever x is, can never be smaller than 3. As a result, we know for sure that this path will still be the better path, regardless of the value of x here, provided that x is non-negative. To put this in general terms, basically if all the edge weights are positive, then as you move forward, the distances can only increase. They'll never decrease, and as a result, we'll never encounter a situation like we had just now, where this edge suddenly becomes better. So this is actually a limitation of Dijkstra's algorithm. You just cannot use it with a graph with negative edges. So that is why we cannot apply Dijkstra's algorithm to a graph that has negative edge weights. So there's nothing left to do now but to discuss the time complexity of Dijkstra's algorithm. Let's take a look. So alright, let's first take a look at the loops themselves. And in this case, we actually have two of them. The main loop of course runs v times, because we start off with a full vertex list, we remove one item every iteration, and we keep doing this until the list is empty. So that's a total of v times. As for the inner for loop, what we're doing here is a pattern we've seen before, and that is every vertex potentially visits every single one of its neighbors. So in total, in the worst case, we'll visit a total of 2e edges. So these are the most important parts. You'll realize that for everything else, we are very much in the mercy of our data structure. Now, as you can see, a lot of the time we actually express our data structures, as if it was an array. But that doesn't mean we can ignore the time required to do that operation, just in case we're going to implement this algorithm without an array. And in fact, most popular formulations of Dijkstra's algorithm does not in fact use flat arrays. Normally, they use some kind of priority queue. In fact, because of that, all these data structure dependent areas in the code are often expressed in priority queue terms. So basically, if we want to express the time complexity of this algorithm in terms of these two operations, then it will look something like this. It's basically v extract minimum operations plus 2e operations of decrease key. We can also express this in a somewhat more professional looking way by expressing it like that. In the simplest case, we don't use a priority queue, we use a linked list, and we'll find that, the time actually boils down to OV squared. However, we can also use a binary heap implementation of a priority queue, and that gives us O E log V. Of course, if we want to go really fancy, we can also use a Fibonacci heap, and that also makes the time difference. And there you have it. That is Dijkstra's algorithm. Now, just one point in note, the original formulation of Dijkstra's algorithm is to actually find the distance between just two nodes in a graph. Now, I think you can trivially modify this algorithm to do that, and all you have to do is, well, when you reach your destination node and when you have confirmed both the path to it as well as the distance, simply terminate. If you have any other nodes, you don't have to visit them. So yeah, the more modern formulation would be to take out that termination condition and use it to find, well, a single source shortest paths to all the nodes in a graph, and that seems to be the more useful result. So that's basically it for this episode. We've taken a look at Dijkstra's algorithm, and we've noted that it has one flaw, and that is the inability to handle negative edge weights. Next time, we're going to continue by looking at yet another single source shortest paths algorithm that doesn't have this limitation. That's all there is for this episode. Thank you very much for watching, and until next time, you're watching 0612 TV. Thank you very much for watching. If you liked this video, consider checking out the rest of my work on my channel. Alternatively, you may want to check out a playlist of the other videos in this series. If you'd like to show me some monetary support, I am on Patreon. You can find a link to my campaign in the video description. Of course, you can simply like this video or leave a comment. I'll be sure to respond as soon as I can. To keep in touch with my future uploads, do subscribe to this channel, and for even more updates, check out the official Twitter account for this channel at 0612TV. Thank you for your support.